Well, welcome everyone. Today we have the opportunity to hear from Dr. Mark Szabo, who's joining us actually all the way from Hungary. Again, sort of that global outreach of Emery Pharma. But yeah, I'm going to introduce Dr. Szabo, who received his PhD from Eötvös Loránd University in Budapest. Again, I'm going to do my best on the pronunciation, so I apologize to anyone if I mispronounce anything. But through his education, he had the opportunity to focus on several different NMR projects, including structure and dynamics of borane organocatalysts and some of their interactions. Following his education, Dr. Szabo's worked as a researcher at Szabo Hungary Limited, where he led analytical efforts really as an NMR specialist. But as an avid researcher, one of his educational achievements includes developing the first online e-learning graduation prep chemistry course in Hungary through the Level Me Up LVLMEUP.HU prep course. So again, expanding sort of that educational outreach. Currently, Dr. Szabo serves as an application scientist at Chemaxon Limited, where he works collaboratively with end users, sales, and software development, including chemoinformatics. He's also serving as an Emery Pharma consultant, primarily as our NMR specialist. Today we have the pleasure to listen to his presentation titled Challenges in Structure, Determination, Thermodynamics, and Kinetics. So please welcome me in joining Dr. Szabo.
So again, thank you very much for the kind introduction. I hope you can see my screen. And so yes, today I'm going to introduce you to 4 short stories about the application of NMR spectroscopy. There will be some tricks how certain structures can be determined, and also how certain thermodynamics and kinetics parameters can be found hidden in the NMR spectra, and which can help us understand certain systems. So these 4 short stories will be the determination of the configuration of symmetrical geometric isomers. So we can determine whether it's a Z or a E configuration. The next one is going to be how certain auto-activating metathesis catalysts could be developed with the help of NMR spectroscopy. The third one is going to be the dynamic systems of frustrated Lewis pairs, and here the emphasis is on dynamic. So I'm going to tell you how dynamic systems can be studied by NMR, and the last chapter is going to be the determination of the relative configuration of certain dirodium complexes. So these are the 4 short stories I'm going to talk about. So the first chapter, the first short story, is how symmetrical geometric isomers, or the configuration of these, can be determined by NMR. And to introduce you to the problem, I'm going to show you 2 molecules. Everyone is well aware of these molecules, maleic acid and fumaric acid. And this is the trans and cis form of kind of the same molecule. So these are geometric isomers. And in this case, in the NMR spectrum, one would see a singlet or a singlet-like peak for the blue and the red protons. Since there is no other protons which are coupled to these. And of course, these are not singlet, these are just singlet-like peaks because these are magnetically non-equivalent protons. But what you would see in an NMR spectrum would be a singlet for maleic acid and a singlet for fumaric acid. If you know the chemical shift from the literature, for example, then you can decide which one is in your sample. But if you don't know it from the literature, then you won't be able to simply figure it out based on the chemical shift. The other thing is that there is a J coupling with the carbon atoms, and there are 1.1% of the molecules where there is a carbon-13, I'm going to switch to the laser pointer, a carbon-13 present in the molecule. And in this case, actually the two protons, the two blue or the two red protons, are not chemically equivalent anymore. And these protons are represented in the satellite peak, the 1.1% satellite peak. And actually this three-bond coupling appears between the two blue or the two red protons. And you can figure out whether it's a cis, so whether it's a maleic acid, or whether it's a fumaric acid, based on the coupling you see on the satellites. This is actually a well-known fact in NMR, so I haven't said anything new so far, but here comes the more interesting part. So the company whom I was working for, Szabo, was specialized in the synthesis of metathesis catalysts, with the help of which the Z homodimers alkenes could be synthesized with metathesis reactions. But here you can see the Z and E isomer. But in this case, in these homodimers, there is a problem, namely that we have methylene groups connected to the sp2 carbon atoms. And these methylene groups couple with the blue or the red protons. And therefore, it's not that easy to read this coupling constant from the satellites, as you will see. But what we can do is there is a technique which is called homodecoupling, or even more sophisticated techniques, which is pure shift NMR. And with the help of these techniques, we can decouple these methylene protons. And what you can see here is actually the signal of this blue proton here. And you can see that it's a triplet-like peak because of the couplings with the methylene protons. Actually, these are just the starting material. It's not that important. It's the middle peak we are focusing on. And when I apply this homodecoupling technique and decouple the methylene protons, I will get a very nice singlet. This is the same molecule, giving rise now to a singlet. Why is this interesting? Because if I zoom in to the satellites, which can be found here, you can see that in the proton spectrum there is basically noise. You are not able to read any kind of information. But in the homodecoupled spectrum, you can see a very nice splitting, which is 10.6 Hertz, which means that in our sample there was the isomer which had the configuration of Z. And we can go further because now we know where the signal of the Z and the E homodimer is. But we can quantify them and we can tell the ratios of the products in a metathesis reaction. And actually I could represent this Z configuration with this emoji and this is the Z configuration with this emoji. So if we work with a regular catalyst, then there will be two peaks, two singulets. This is already a homodecoupled spectrum. And we already know that the left one is the E and the right one is the Z configuration based on the satellites. And actually we can tell the ratio right now. It's 76% E and 24% Z, which means kind of a thermodynamic equilibrium. Actually, without homodecoupling, I wouldn't be able to integrate these two peaks because these would heavily overlap. And when using the company's catalyst, then actually we can get 95% Z configuration in the end. So this was the first chapter where I used homodecoupling to be able to differentiate between Z and E isomers of homodimer alkenes. Actually, I think there is no other technique with which you can figure out the configuration. So definitely LCMS or GCMS wouldn't be able to do it. If you have the Z configuration and you know that it's the Z, then you can measure a retention time and then you can use LC-MS or GC-MS. But to figure out which configuration is there, you need NMR. Let me go ahead to the second chapter, which is about how certain so-called auto-activating metathesis catalysts have been developed at Szabo. Actually, these metathesis catalysts can be used to create those homodimers I've been talking about. So let me introduce you to these structures. First of all, there are well-known 14 electron shock complexes, which are very effective catalysts in metathesis reactions. But the problem is that although they are very active, they are not very stable. They are air sensitive, they are moisture sensitive, and it's very hard to work with them. And what Fürstner did, he's a researcher in the field of metathesis, is that he created 18 electron adducts with the so-called phenanthrolene, which are not active anymore, but are stable. And actually, phenanthrolene, and therefore the 14 electron complex, can be liberated with additional Lewis acids, like for example zinc chloride. This is actually a one-way reaction. It's not an equilibrium system. You can see a very, very high equilibrium constant. So basically, it's shifted to the right. And what we did at Szabo was that we used tungsten complexes instead of molybdenum, which are a little bit weaker Lewis acids. And we used bipyridine ligands instead. And what we gained is an equilibrium system. Here you can see the equilibrium constant of the system. So actually, we made these complexes, these 18 electron complexes, auto-activating, because if you put them in solution, they will automatically dissociate, and the active complex will be there to do the reaction for us. And one driving force behind this dissociation can be that actually this antiperiplanar conformation of bipyridine is way more stable than this one on the left, so this can be a driving force of dissociation. And what I did here with NMR is actually I made several one-dimensional proton measurements at different temperatures from 25 to 70 degrees. And what you can see here is that here is the signal of the free complex, so the free 14 electron species. This is actually kept at constant intensity. But as you can see, when we heat up the sample, there is less and less complexed 18 electron species, and the system is more dissociated. And actually, this is what we expect when we heat up a complex, that it's going to favor dissociation. But actually, by integrating the complexed 18 electron signal and the 14 electron signal, I can calculate, based on this very simple equation, I can calculate the equilibrium constants at each temperature. From the equilibrium constants, I can fit a very nice linear, and the parameters in this linear is actually the enthalpy changed and the entropy change, from which I can calculate the Gibbs free energy. And actually I did this for several compounds, and this is a very nice thermodynamic parameter which can tell you actually how these systems are going to work, and actually, for example, at what amount will be in the dissociated form at a given temperature. So these are very nice properties what you can calculate from simple one-dimensional spectra. And actually, again, there is probably no other technique with which you can calculate such properties that easily and that and in such an elegant way, I would say. So let me jump to the third short story, which are the moisture-tolerant frustrated Lewis pairs. And again, let me introduce you a little bit to the topic. And let me start with what are these frustrated Lewis pairs. Actually, these are Lewis pairs where there is a steric hindrance, so there is a bulky Lewis acid and a bulky Lewis base, and therefore these are high energy systems, meaning that they can be used to activate small molecules and catalyze, for example, hydrogenation reactions. And one well-known Lewis acid, which is used in the field of frustrated Lewis pairs, is this 3-pentafluorophenylborane. And again, the problem is, just like in the former case, is that it's moisture and air sensitive. And our solution, again, was that we should create weaker Lewis acids. And how we reach this is that actually we decreased the number of the halogen atoms on the rings. And you can see that we synthesized 3 boranes, and in the first case there are 3 fluorines and 3 chlorine atoms in the system, all of them in the ortho positions. And then there is a ring which has 2 chlorines, so there is only 2 fluorine atoms in this borane. And in the last one, there is only 1 fluorine atom and 2 rings containing 2 chlorines in the ortho position. And what we did is that we tested all these 3 boranes in the reaction, what you can see on the screen. And the interesting part of this reaction is that this is a reductive amination reaction. And one of the products is water. And if you remember, this is a moisture-tolerant catalyst, or at least 3-pentafluorophenylborane was. And we applied 10 mole% of the catalyst. So actually 10 times excess was formed from water. And here you can see in the table the results of the test. And actually the first molecule with the 3 fluorines performed pretty well, we can call this well, at 80 degrees in 72 hours, the conversion was 78%. The second one, which had less fluorines and more chlorines, performed even better. It was 99%, the conversion. And the third one performed just as well, it's 99%, but as you can see, it worked even when there was no molecular sieves in the system. So you can clearly see that there is a difference in the efficiency of the catalysts, and we wanted to understand what's behind this difference with the help of NMR spectroscopy. First of all, what we did is that we put in our sample the borane, the non-coordinating Lewis base, and some water. And we cooled down the sample to minus 30 degrees. And actually, there is a very interesting thing here. You can see that the 2 protons of the water give rise to 2 different signals in the NMR spectrum, one at around 4 and one at around 13. And then I thought that I should measure a dose spectrum. And the result of the dose spectrum, what you can see on the y-axis here, is actually the diffusion coefficient of every species present in the sample, which is related to actually the size of the given species. And what we can see is that the 2 protons of water, which can be seen here, because on the x-axis you can actually see a hydrogen spectrum, a proton spectrum. So the 2 water signals, the signal of the DOPCO, the base, and the signal of the Lewis acid, the borane, all have the same diffusion coefficient, which means that they are connected to each other, they are coordinated to each other. And to prove that with another technique, I also measured the noisy spectrum, and you can see that the protons of water and WAPCO, indicated with these green circles, are close to each other in space. Meaning that we have a complex like this, a ternary complex, where water is coordinated to the borane and WAPCO is coordinated to water. And actually that is why there is two different signals of water, because to one proton there is a nitrogen coordinated and the other one is kind of free, it's not coordinated. Okay, so now we understand how this structure looks like, what is present in our sample. But then I realized that in the proton spectrum, I can see the complexed signal, so the signal of the complexed borane and the signal of the free borane. And I integrated these two at several different temperatures, from minus 30 degrees to 40 degrees. And it turned out that in the case of borane number 1, where there are 3 fluorine atoms and 3 chlorines, there were no free borane at any of the applied temperatures. In the case of the other two, so borane number 2, which contains 4 chlorine and 2 fluorines, and borane number 3, which contains 5 chlorines and 1 fluorine. So in these cases, the free form, the ratio of the free form was very similar. So actually, this doesn't explain why borane number 3 was more efficient than borane number 2. But this certainly explains why borane number 1 was not that efficient, because there is almost no free form available, and actually the free form has to be there to do the catalysis. So the next step was that I measured an EXI spectrum, which is basically a noisy spectrum. It's the abbreviation for exchange spectroscopy. And you can see here two cross peaks in the spectrum, which means that the free form of the borane and the complex form of the borane are in exchange. And actually, from these measurements, you can extract the exchange rates in the case of both of the borane in question. And I would like to show you the values at 35 degrees. And you can see that the exchange rate is almost 20 times higher for the borane, which contains more chlorine atoms. And actually, this is what explains the difference in efficiency. And what's behind this higher exchange rate? It's actually the so-called backstrain, the higher backstrain. And what is backstrain? It's that when something is coordinating to the borane, then the borane becomes trigonal pyramidal instead of a flat structure. And as it becomes trigonal pyramidal, the chlorine atoms, which are certainly bigger in size than the fluorines, create a higher backstrain and pushes back the borane. And this is the driving force of the dissociation. And this is what's behind the higher dissociation rate present. So this is, I think, the major advantage of NMR over any other structure determination tool, let alone LC-MS and GC-MS, that here you don't see some static images of your system, but you can measure the dynamics and you can see what is happening in the solution. And actually you can do this to several different time scales. So it's a very wide time scale what you can investigate. And now let me jump to the last short story, namely the identification of relative configuration of certain dirodium complexes. And again, I start with an introduction to the topic. And I'm going to start with the dirhodium tetraacetate. You can see the structure of this molecule here. It actually has this so-called pedal wheel structure. And there are 4 so-called equatorial sites. Here you can see these acetate ligands, which are bridging bidentate ligands. So they are creating a bridge. And there are these so-called axial sites, where certain molecules, mostly solvent molecules, can coordinate to the rhodium core. And in our case, the solvent was always acetonitrile. And actually, why are these interesting molecules? Because these, again, can be used as catalysts in several organic syntheses. For example, cyclopropanation. So what we did with this dirhodium tetraacetate is that we reacted it with amino acids, different kind of amino acids. And what happens in this reaction is that 2 of the acetate ligands can be exchanged to amino acid ligands. But as you can see, the acetate ligand was a so-called bridging ligand. But the amino acid coordinates as a chelating ligand. So this is something like what we call a twisted paddle wheel structure. And you can see the 2 amino acids coordinated to the rhodium core. But as a result, the rhodium core actually becomes chiral. We call this inherently chiral. And actually the configuration of the amino acid predetermines what the configuration will be at the rhodium core. And these are actually mirror images, what you can see. So the configuration is lambda. We call this configuration lambda. When we go from the oxygen to the rhodium to the rhodium to the oxygen, this is a dihedral angle, and this dihedral angle is negative. So then we have the lambda configuration. In the other case, when the oxygen, rhodium, rhodium, oxygen is positive, the dihedral angle is positive, then we had the delta configuration. But what amino acids we used were either N-substituted or proline amino acids, meaning that when these are coordinated to the rhodium core, actually not just the rhodium core becomes chiral, but also the nitrogen atom. Meaning that I have to figure out the configuration of the rhodium core and the nitrogen atom, knowing the configuration of the amino acid. So let's say that we know the configuration of amino acid, which is R. Then there are 4 possible diastereomers because the nitrogen atom can be S or R, and the complex can be lambda or delta. So these are the 4 possible isomers, diastereomers. And actually, there are other methods with which someone can figure out the configuration of a given compound. And these are chiroptical methods. But without going into the details, the problem with these methods are that this takes a lot of time. And it would be better to solve it with NMR. And that's what I did, actually. But before I measured any spectra, I actually made I'm really fond of making some quantum chemical calculations. And it turned out that the S lambda diastereomer is way more stable than any other. So probably what we have in our solution is S lambda, but let's check it with NMR. So first of all, just there is an interesting spectrum here, which is a so-called 15 nitrogen HMBC spectrum. And you can see here that the free amino acid, in the case of the free amino acid, the nitrogen shift is 68. In the case of the complex amino acids, it's 8. So actually there is a 60 ppm difference, and this is confirming, this proves us that the amino acid is coordinated through the nitrogen atom. If we check out the proton spectrum of this molecule, then we can see that the NH is here, the alpha H is here, and these are very sharp signals with visible J coupling, which is 12.1 Hertz. And actually this coupling can be translated by the Karplus equation into certain dihedral angles, which actually tells us that the configuration of the nitrogen is indeed S, just like the quantum chemical calculation told us. Again, this is a relative configuration because I knew what the configuration of the carbon atom was, but I could determine the configuration of the nitrogen based on this information. And then I was sitting in my chair and I was looking at this 3D structure of the rhodium complex, and I couldn't find any spatial proximities which would prove whether the rhodium core is lambda or delta. If I was able to find such proximities, then I could just measure a noisy spectrum and figure out which configuration is present. But there was no spatial proximity like that. But at this point, I would like to remind you that there is an axial position of these compounds. So certain molecules can coordinate to the rhodium core. And that's what I wanted to exploit. And this is what can help me to figure out the configuration. The only thing is that it has to be, whatever the molecule is, it has to bond stronger to the rhodium than acetonitrile, which was our solvent, and which is a deuterated solvent, so I can't use it to measure any spatial proximity. So what I did, again, is that I calculated Gibbs free energy of complexations. And based on this, I figured out that pyridine, for example, coordinates way stronger than acetonitrile. These are the Gibbs free energies of complexation. So what I did is that I doped the sample with some pyridine. And actually, indeed, pyridine bound stronger to the rhodium core than the solvent. And I could exploit this. Here is the proton spectrum of the molecule. Again, you can see the alpha proton and the NH. And since I doped it with pyridine, here you can see the orthoproton of pyridine. And what I did is I measured a one-dimensional noisy spectrum, meaning that I selectively excited this peak, the pyridine orthoproton. And the result is that there is no signal where the NH proton should be, but there is a strong signal in the noisy spectrum where the alpha H is in the proton spectrum, meaning that the alpha H is close to the pyridine orthoproton, while the NH is not close to it. I try to show this to you in this three-dimensional structure. So this is the orthoproton of pyridine, and actually you can see that this is very close in space to the alpha proton. Here you can see that the nitrogen is coordinated to the rhodium core, and here you can see the NH, and you can see that the NH is not close to the orthoproton, and that is what can be seen in the noisy spectrum. And actually there is a very simple decision table that if there is no NOE with the NH, but there is some NOE with the alpha H, then this must be the S lambda configuration. So here I could exploit that a certain Lewis base can coordinate to the rhodium core, and upon coordination there are spatial proximities which proves the configuration of the complex. Again, NMR is way more superior to any other techniques because these are very simple measurements, can be carried out in a couple of minutes, and one can get the information really fast. So what I wanted to tell you with these 4 short stories is that most importantly that NMR is an extremely versatile tool. You have several experiments and you can always find a way to figure out how your structure looks like in solution, and even the dynamics or the thermodynamics of these systems. So I managed to figure out the configuration of homodimer alkenes by applying certain homodecoupling techniques. I could extract equilibrium constants from the system using dynamic NMR measurements, so variable temperature NMR measurements. And these constants were important because these are related to the stability and effectiveness of the auto-activating catalysts. I was able to characterize frustrated Lewis pairs. I could figure out the structures and the dynamics behind the scene, which explained why one of the catalysts is superior to others. And I managed to figure out the configuration of certain rhodium complexes. And with this, I would like to thank you very much for your attention, and let me know if you have any questions.
Thank you very much. On the organoboron chemistry, Mark, do you know how they were synthesized actually, the boranes? These are pyrophoric molecule, and I assume the ones that are sterically not so hindered, they would even be more pyrophoric, the fluorine.
So actually I don't remember how these were synthesized because I wasn't part of the synthetic team. However, these are published results, so I can send you the paper. It's actually in Angewandte chemistry, and there is the synthesis there, so you can check that.
Wonderful, and it looks like the best efficacy you had was in terms of that formation of the amine. The secondary amine is through the highly chlorinated.
Exactly. And the reason is that the chlorine atoms are bigger, and this creates a higher backstrain, which actually makes the system more dynamic. And that's the reason behind it.
Yeah, thank you. Any other questions?
Yeah, so a great presentation. In terms of maybe, people always talk about some of the limitations with NMR. You talked a lot about, dynamic NMR or like the homodimer analysis. Can you maybe speak to some of the potentials or the limitations for quantitation and the capabilities that you're able to do?
The limitations in quantitative NMR, or the limitations in NMR in general?
Yes, both.
Okay, so I think the limitation of NMR is mainly that you need, let's say, high amount of structure, a high amount of the given molecule. So you can measure a proton spectrum with 1 or 2 milligrams of the compound, but other than that, you need way more than that, let's say 20 milligrams to measure proper carbon atoms. Of course, it depends on the molecular weight. And you have to be able to dissolve it in some kind of solvent. Otherwise, so solid state NMR is a whole other topic. So that's why you have to be able to do this. I think these are the main problems. So that is why, for example, NMR is not so good to really investigate very complex mixtures, for example. It's better when you have a single, let's say, pure compound. Yeah, I would say this is, and when we talk about quantitative NMR, the problem is actually the same, that you need let's say a lot of sample, and also that quantitative NMR can take a lot of time because you have to wait enough for the sample to relax, but I think it's still one of the best methods to quantify a certain molecule or a certain sample.
Thank you. I guess so. Yesterday we actually had an interesting, discussion about diffusion NMR, and because you had just mentioned, some of the challenges with quantitation in complex mixtures. Can you maybe talk a little bit about how diffusion NMR could potentially solve some of those challenges?
Yeah. So in diffusion NMR, let me come here. So this is, for example, a dosy spectrum. So it's nice because you can. This is actually like chromatography. So you can see that the solvent toluene and the signal of toluene is at a different position in the Y scale that the signal of the complex. So this is actually a good technique to investigate mixtures, but the problem is that when you have overlapping signals, then you won't be able to actually measure a meaningful dosy spectrum, because either you will get a signal which is somewhat the average of the two, I mean the diffusion coefficient, or you will get some kind of signals which are really hard to interpret. So to really investigate on mixtures which has several components, you can do this by dosy, but you need well-defined separated signals of each component in the mixture.
Thank you.
Thank you so much. Thank you, Mark, and look forward to working with you. And let's give him another round of applause.